Right. Thank you, Eugene, for the nice presentation, and thank you, everybody, for being here. So, yes, I am a research fellow at the Knowledge Media Institute of the Open University. Today, I'm going to talk about knowledge organization systems of research field. And the reason why I am is because I recently published a survey that includes 45 KOSs of research fields and discussed through them what are the challenges, what are the gaps. But in order to keep this session a little bit more practical, I'm gonna reduce the theoretical concepts and theoretical level of things, but introduce a little bit more pragmatic stuff. Some of the research I've been doing in the past few years with regards of KOS, but also in a way to generate them. So yes, I work in the scoring knowledge mining team, and our work is introducing AI solutions in order to perform meta science, to analyze, to get insights from scientific data, and try to support companies and also policymakers. We have been collaborating a lot with several organizations and companies too. Okay, what's the promise from today? For today, I will give you a status quo for knowledge organization system of research field. We will also learn about what are the challenges and opportunities that the community is currently facing, how AI can support the generation of these knowledge organization systems, and what is our lesson learned, the lesson learned that I want to share with you. And I want to start with a little bit of motivation, why I am here today, or in general, why I've done this work and I am today presenting to you. So it dates back to 2018, 2019, when we released the computer science ontology. We developed this with our team. The computer science ontology is a large-scale, automatically generated ontology of research topics in computer science. It includes 14,000 topics and 163,000 relationships. And it's very fine-grained, and it connects research concepts according to the very usual relationships, like whether a concept is a father than another, and there are similar concepts and so on. Very, very simple. It organizes the computer science field through a taxonomical, polyhierarchical taxonomy. And for us, the natural step, once we developed this, was to develop the CSO classifier. Sorry for this shameless advertising, but I think it's really important to show a little bit the background so that we all understand where I come from, right? So the CSO classifier, it's a tool, it's an application that you can easily install. It's a Python library you can install by running pip install CSO classifier. What it does is taking research papers or any technical document in computer science and giving you as output research concepts. So and then when you have the computer science ontology on one side and a tool to annotate your documents, basically you unlock all sorts of things that you can do with a data set that has been annotated with research topics. And coming from the field of meta science, for us is, for example, analyzing trends, analyzing organizations and stuff. And from there, we moved onwards by developing the AIDA dashboard. The AIDA dashboard is a tool for exploring and comparing scientific venues, conferences, and journals in particular, and does this analysis through all the research topics, analyze authors and everything. So it's a very compact view of stuff. And you can understand, for example, what are the main topics that have been discussed in a conference or in a journal. Moving forward, we did some other analysis. For example, we analyzed how topic evolved over time. So where the research flew, how the research flew through different stages. For example, was it born first in academia or in industry, then it moved from one side to another? Was it first published in papers or then in patents and so on? And this is important. This is, you can start appreciating how an ontology of research topic is very important here, because once you have characterized a research topic and you are able to understand what are the papers associated to each topic, especially if you have a division over time, like characterization of them over time, you can see how they progress, how they move from academia and industry, whether there is collaborative effort and so on. Another exercise, and this is the last one, is this characterizing, for example, research teams. So we looked at research teams and we understood exactly how is the extent of the diversity of expertise, how many different subgroups of people are in there. Is it true that different teams with different different sub-teams with different expertise actually lead to a higher impact? Well, we have evidence, we have done an experimentation, we have evidence that whenever there is, in a research team, there are subgroups with different expertise, then their paper is likely to attain higher impact in the following 5 years. So now that I've showed to you what is the potential of having all these kind of things, we started wondering, okay, we have done all these amazing things in the field of computer science, right? Now, how do we move towards other fields of science? And of course, the simple question there is, well, you need a new taxonomy. For example, if we want to move in engineering, you need a taxonomy that characterizes topic of engineering, right? And of course, the process of developing new one is very tedious because developing the CSO is expensive. It takes a lot of time and so on. It's not easy. Is there something that we can, off the shelf, take and reuse? Well, that's why we started thinking about, okay, let's do a survey on knowledge organization system like taxonomy and ontologies of research topics. And that's where the whole conversation that we're having today comes from. So we have this paper, which has got recently published at Quantitative Science Study. Here you find the DOI, you can scan this. Anyway, I'm sure you will get the slides at some point, and you will be able to read the paper. But again, I will not dive into the theoretical aspect of everything. I will just describe a few things in I will likely touch some stuff, and then I will provide more practical aspects, like a sort of consequences of this survey. So what is this survey about? Very briefly. So I know that you guys are expert in knowledge organization system, but in order to be inclusive, I want to make sure that everybody's on the same page, with me at least. So knowledge organization system, you can see it as a sort of dictionary of terms that organizes the different terminology within a research field. In this particular case, in computer science, you have all the topics: computer science, artificial intelligence, machine learning, and how they are organized, right? For example, computer science is father of artificial intelligence, which is father of machine learning. And yes, so there could be, here I put a reference from Marshall A. Zhang, which describes beautifully, I really enjoyed reading that paper, describes beautifully different version of knowledge organization system that you can find. And of course, they range from functionality and also from expressiveness. You can start from a list of terms, which is just a collection of terms, no relationship whatsoever. Then you have taxonomies, which adds hierarchical terms. Then you can have thesauri, which add, for example, related terms. And then you can have ontologies, which basically help you to model anything you can think of, because the sky is the limit in this case. So why KOSs are so important? Well, of course, they are important for digital library. They help organizing information, augment retrieval, recommender system, and so on. But also in information science, because, for example, as I showed you some cases, they allow us to analyze the research landscape and, for example, do trend analysis, forecasting, team composition, and also analyze research impact, which is a very, very big topic. Now, the retrieval process, well, we use several strategies. We queried Google Scholar, we analyzed websites from academic publishers, for example, also preprint archives and academic search engines like Archive, Springer Nature, Elsevier, and so on. We queried Google because at some point that wasn't enough. We contacted colleagues from the digital library, that community that we met at JCDL and TPDL. We also looked at Wikipedia. Actually, Wikipedia turns out to be a very good repository, well, I mean, sort of dictionary where all of them are collected. It's very extensive. We also explored external links because, of course, these courses are interconnected between themselves. And also we contacted professors in the missing disciplines. For example, we contacted professor from history saying what kind of course to use to organize your paper. So we analyzed them according to 15 features. And here they are kind of grouped according to the scope, for example, the structure, the curation, external link, and usage. So for example, for the structure, we looked at the type of system. Are we talking about taxonomy, a thesaurus, an ontology, a term list? What are the number of concepts they have? What is the depth? What is the kind of hierarchy they have? Is it monohierarchic, polyhierarchic? Do they have related terms? And so on. But for today, I will just provide another view on a few of them, not all of them. The ones that I consider most important. So as I mentioned to you earlier, we found 45 of them. 23 are focusing on single field. So for example, we can find the Agrovoc thesaurus, which heavily focuses on agriculture. The computer science ontology, like our own, focuses on computer science, while there are 22 of them that are multi-field. For example, there is Eurovoc, the UNESCO thesaurus. You might know, for example, the Open Alex topics, which span across the whole kind of digital library they have. Now, with regards to the scope, there are several fields that have, for example, multiple knowledge organization systems. For example, medicine has got UMLS, also MESH, and so on. But there are also single field that, like disciplines that do not have their own one. So, for example, material science, geography, history, they do not have their own one. They may have some concept in other ones, but specific for this discipline, we couldn't find any. And with regards to the multi-field course, what we found is that even though they kind of aim to cover all disciplines, actually there are a lot of spots there where they actually fail to cover certain discipline, or they partially cover them, or they just even mention the discipline. So you can see that here the scenario is a bit kind of spotty. With regards to the number of concepts, we have a very highly heterogeneous scenario. We have, for example, the Ford from OECD, which has only 48 concepts. And then we have, on the other end, we have biomedical ontology for Bioportal, which contains 13 million concepts. So here we have a very wide scenario. And what happens is that the median of this is 4,700 concepts, and 16 single field courses are above this median, and 16 multi-field courses are below this median. This suggests, and we will see it later also, this suggests an interesting phenomenon, which means that single field ones are usually very specific, comprehensive, they're very large, and they try to look at all the nuances of a particular discipline. Whereas for the multi-field ones, they're usually generic, they're very broad, and they focus on the top level, the topics. They don't go in detail. So there is this kind of like double distribution in a way. And this is also visible when we look at the depth, for example. So we have the Web of Science category that have only one level. It's just a list of topics, basically. They don't have any relationship. And then there is, for example, the Open Biological and Biomedical Ontology that's got 39 levels. So can you imagine? You have like 39 descendants. And the median here is 6. And what happens is that 18 multi-field courses are below the median. So again, what is happening here, what is this showing to us? That is the multi-field one that typically encompass multiple disciplines, are typically very shallow. They're superficial, they focus on the top field, but they don't go into detail. I guess because maybe the objective of the curator is let's focus on, on kind of amplitude rather than depth. Generation. So we have that the majority of them are manually curated. There is a starting kind of trend in which more and more communities are developing them more semi-automatically, automatically, because people understood the need of having a comprehensive ontology, or KOSs. I'm using this ontology, KOSs, and taxonomy in a way interchangeably, but what I'm talking about is knowledge condition systems. So please bear with me if I'm using different terminology, also to diversify a bit. So there is a trend nowadays to produce them more semi-automatically and automatically, because people have understood that there is a need of such a KOS that kind of serves different purposes, and it's both covers multiple fields, but also goes into the depth of the different fields, right? So, for example, OpenAlex topics, the computer science ontology, also OpenAir have been developed automatically, and or semi-automatically, I should say. And also there are also community-based ones. So, for example, FISH, the physics subject headings, also MESH, the medical subject headings are community-based, so they are welcoming feedback from the community through different strategies. For example, GitHub issues, or on a forum, or you can submit a case for including a new topic. Distribution formats, as you can see here, there are these KOSs are distributed in a variety of formats. Typically, in our analysis, we could identify four main ones. For example, RDF, which is the resource description framework, which is used for releasing ontology. So it's for kind of serializing ontologies. Then there is, of course, CSV, HTML, so simply a page on the browser, and the most brutal one, it's just on PDF. So 24 of them are accessible via the provider website. HTML, we can argue that HTML is machine readable, but not really machine interpretable, because typically these are just concepts in a page, but it's very hard to infer the relationship between concepts because they're just displayed. They're not really interpretable in a way. They're not fair. They're not findable. I mean, they're not interoperable in this way. Some of them, more machine readable formats include, for example, 10 of them are released in CSV and 17 in a resource description framework, the one that it's a standard that I mentioned to you earlier. The very negative note is that 6 KOSs are only available in PDF. So it's very challenging for the point of view of reuse. External links, 19 of them are connected to other KOSs. So some of them connect to other KOSs that are available. So for example, Agrovot connects to UNESCO and so on. They connect to each other. So typically this is achieved unidirectionally, but of course, maybe the other one that is already the receiving end might say, okay, I might connect you back. So Wikidata is the knowledge base that is the highest with the inbound links, meaning that most of those KOSs that we analyzed typically tend to connect to Wikidata. So they like to have Wikidata at the center of this blob of KOSs, right? And for example, Agrovoc, Chemont, STW Thesaurus are the KOSs with the highest outbound links, are the ones that provide a lot of links to external resources. And this is good because once you can integrate different ones, you can achieve this sort of interconnected network of KOSs. Now, this is the overview I wanted to give. Now I want to quickly move on the challenges. There are 8 challenges that I want to quickly highlight. And so yes, the first one is that, as I mentioned to you, this is a bit of a gap, actually, a gap connected to a challenge. To this day, we have a big gap, which is there is no KOS that is comprehensive, which includes all fields of science. It's granular, so it goes very deep in representing all the nuances of a field. It is open, so for people to reuse it freely, of course, and it is maintained. Because, of course, one of the problems of manually updating KOSs is that they typically tend to outdate unless there is a consortium behind that keeps them updated. But without this, typically they tend to outdate, especially because when they become big, they're very hard to maintain. So anyway, I'm diverging a bit here. But anyway, to this day, we don't have any KOS that fulfills those 4 characteristics. And I mean, it's a gap and it's a challenge. I believe we should move towards this kind of opportunity in developing this KOS, because then it will be transformative, and it will unlock a lot of potential for downstream applications. We need to integrate multiple KOS. At the moment, there are some links, as I mentioned to you, but they're not complete. These links can be done manually, semi-automatically, or automatically. We can use RDF, for example, because RDF naturally is able to describe those kind of links, to describe like similar concept across different KOS. However, not all KOS are in RDF. And then we can develop tools for facilitating integration of KOS. Improving the language coverage. So some KOS, I skipped this, but some KOS are available in multiple languages, not all of them. And this is crucial for interoperability and cross-language exploration and exploitation of digital artifacts. Because, for example, maybe there is a repository in Hungary. I'm just pick one name of a country, and maybe it contains data sets that are described using topics in Hungarian language, right? And unless there is a direct translation of that KOS in English, it's not going to be very interoperable. Or maybe there are students that are not familiar with a language, and they might find quite hard to explore a digital library, for example. There have been some efforts. For example, Agrovot has got international institutions that is authoring translation. So Agrovot actually is the KOS with the highest number of languages. It's amazing. They just delegate translations to different institutions. So with this kind of divide et impera solution, they're able to maximize the language coverage. And nowadays, of course, we can try to use LLMs to kind of cover languages that in a more quick way. Reconciliating expert disagreement. Of course, everybody comes with their own background. Everybody has got their own opinion on how fields should be located and connected between each other. So we need tool to mitigate this disagreement. And also we need to assess the quality of KOS, which is a challenge. And of course, this quality can be at the structural level or at the conceptual level. Structural level is that maybe there are inconsistencies or contradiction. Maybe, two topics are saying the opposite thing, like the connection between topics. There is a connection that says that one topic is broader than another, and then there is a connection that says that the same two topics instead are in a narrower relationship. This is a sort of inconsistencies. But for the conceptual level, at the conceptual level, we need to look for accuracy and completeness. And actually, completeness is a very big challenge. And also accuracy. We will see a little bit more later. Also handling ambiguous labels, because, for example, Mercury can be a planet, a metal, or even a Roman god. So polysemy, it's there. It's an issue. And there are strategies that come from the semantic web field, for example, making sure that concepts have got their own type, and in this way it will be a solution. However, there are still challenges there. Automatic generation and updating of KOS, more to come in this presentation. So there are various initiatives, as I mentioned to you earlier, because we can build, for example, KOS either from scratch or extending the existing one. So we are currently exploring some solution. I will show you more. And of course, the last but not least is that there are some challenges in annotating research artifacts with respect to their KOS, or with respect to different KOS. Yes, we have successfully built this in the field of computer science, but other fields do not have that. LLM seem to overcome this current challenge, but opens to other challenges, for example, scalability, cost, and sustainability. They are quite expensive to run, they burn forests, as many people would argue, and it's impractical. So we need to find something that is a bit lightweight and works also in a fast way. Okay, concluding the first bit, because then I want to move to the second part, is that in this survey, and we analyzed 45 KOSs, 23 of them are single field, 22 of them are multi-field. We analyzed through several features, 15 to be precise. 7 of them are without their own KOS. So this discipline do not have specific KOS that describe all the different fine-grained topics. 32 of them are developed manually, although the wind is changing. Many initiatives are starting to arise in developing them semi-automatically or even more ambitiously automatically. And the gap is evident. There is no comprehensive, granular, open, and regularly maintained one. And this is my call. Like, we should use the latest developments of AI in order to kind of bridge this gap. Okay, so now I want to show, now that I've just given you an overview of the survey, I want to keep it short and very to the point, just because I wanted to show you a little bit of things that we are doing in our team, which is AI-generated KOS. So the first algorithm that we ever developed is called Cling2. And this allowed us to develop the computer science ontology that I mentioned to you at the beginning. And the way it was working was simply using statistics. It would take a corpus, it will take the keywords of the papers and try to look, okay, what are the occurrences of, it will try to establish connection between pairs of topic, right? Because this is the task. You have different topics and your objective is try to identify whether between each couple of topics, each pair of topics, there should be a relationship, right? But also, what is the relationship, right? Is it like a sort of hierarchical one, or is it a related one? So the way we were doing this was simply looking at the statistics. Let's look at how many times each concept appeared in the literature, in the papers, right? And how many times they occur together. And based on this information, we will be able to establish whether there is an overlap between the two topics. If there is an overlap, then maybe the two topics are hierarchical, and the smaller one is the child of the bigger one. And if instead the two topics are more or less like on the same sides or similarly syntactically, and we would also use information from Wikidata and Wikipedia, then we could, for example, establish a cluster, a synonym ring, right? So through these kind of solutions, we will develop the computer science ontology, which included only 3 relationships, broader generic, contributes to, and related equivalent. Now, this was 6 years ago, let's say, 2018, 2017. Now the technology has evolved. We have seen a lot of development in AI, and we said, okay, let's try to be a little bit more precise, and let's try to use one of the latest technologies. So we have developed this pipeline, which includes, so try to generate something with more traditional AI rather than simply statistics. Although at the end of the day, AI is statistics, but that's another story. So the pipeline consists of 3 steps. Topic extraction. So you take all the papers and you extract the topics from the paper. So we develop a tool that extracts the entities, and these entities are research concepts. Then again, relationship classification. Given a pair of concepts, what is the classification that would hold between these 2 concepts? And then, of course, finally, ontology construction, which is basically setting up the whole network so that it could be displayed and be used, especially also because the ontology construction is a bit of more post-processing. For example, there are inconsistencies, or we need to clean it up, we need to filter some stuff, and so on. So that's why we materialize this last step. But here, I want to just focus on the central bit, the relationship classification, because in our kind of research, we found this bit kind of hard and challenging. So what we did was, for each couple, we used Cybert. And what we did was we fine-tuned it. We actually did not use only Cybert. We only used other things, other models. We fine-tuned this model. We trained this model on, okay, given a gold standard, you have topic A, topic B, and the relationship. And the relationship will be supertopic, subtopic, same as, or not related. We will train our models and eventually test it. So here are some results. So we use gradient boosting, random forest, and in general, what we observed is that language, like Cybert in this particular case, is particularly good once it is fine-tuned in identifying the semantic relationship. So, for example, on average, it will get an F1 score of 91%, which is quite good. However, it's not all gold, because and this is our first lesson learned, because even though performance are excellent, right? We got 91%, it's amazing. Some issues emerge when we create the final resource, when we create the ontology. And what we observed is that even a few misclassified relationships could introduce really hard to find inconsistencies. As I mentioned to you earlier, for example, you have a chain of topic. A is parent than B, B is parent than C, and C is parent than D. But then all of a sudden, the classifier misclassifies and says that D is parent than A. So what you have effectively done is to build a loop. Now, how do you break it? That's the challenge. So you can see that because of one simple wrong link, you have created something that is useless in a way. I don't want to use this strong word, but to simplify it, right? So it's very hard. Those inconsistencies are hard to tackle. This is something that we are currently facing. We are trying to adjust the model. And so this is what is teaching us, is that this task, kind of classifying the relationship between pairs of topics, is highly sensitive to the performance. Even small imperfection can have a large and negative impact on the quality and usability and correctness of the final resource. So we started also introducing additional statistics. So because, of course, we moved from statistics to traditional AI, we said, okay, why don't we merge the two of them and try to see whether we can get better results, right? So we started including occurrences in the fine-tuning, also the concurrencies. We obtained better performances. This is still a work in progress. Here I'm adding at the bottom a reference that you can look at if you want to, and if you have feedback, feel free to send me an email later. Any feedback is very much welcome. Now, this is not over, because in another effort that we are doing, we are using large language models. So we use traditional AI. Now let's use generative AI. Let's see, is generative AI any better, right? So what we are doing here is try again relationship classification, the second step in the middle, using zero shot. And what we are doing is that, again, giving a pair of topic A, topic B, we employ a multi-class classification to determine the semantic relationship. So we have developed a few strategies here. I'll try to walk you through, and hopefully, finger crossed, I will be good to not confuse you. So what we do is simply, we create a prompt, we use a template, we ask the LLM, and we pass the response. However, this is standard process, right? Standard process. Prompt, LLM, response. However, we didn't stop there, because, broader is the opposite of narrower, and same-as is kind of inverse, is kind of it's an inverse relationship. If two topics are same as, of course, the other relationship is going to be true, right? So what we did, okay, let's query the model twice. Maybe we switched topics, we swap the topic, and basically we do the same process. Do they agree? Is the model consistent? So these are the kind of questions. So what we have at the end is a referee. It's a sort of rule-based mechanism that says, okay, if f dx, the first branch says that it's the relationship is broader, and the second one that says that once it's swapped says that it's narrower, okay, thumbs up, it's a good one because the 2-1 are consistent. So it says that the topic between A and B is broader. Right, so we developed this sort of rule to mitigate this kind of disagreement or agreement. Anyway, so this is the first one. However, yet is not finished, because then we have another strategy, which is a bit using chain of thought. I don't know whether you're familiar with chain of thought, but it's a framework that helps the model, the large language model, to think, to reason about, because think is not the right word we should use, but to reason about a particular task. And then basically once the reasoning is over, you take everything and then you ask the task. In this particular context, what we did was we asked to, in this context, we say, okay, define the topic, formulate a sentence, and then start discussing about what could be the potential relationship between the two topics. And then we feed it back everything into the model, and we say, okay, now tell us precisely what is it. And of course, also here, since we are here, in for a penny, in for a pound, we did the swap thing, and we used also the two-way strategy with the referee again. So essentially, or effectively, what we have here is that we test 4 strategies, standard prompting, one-way and two-way, and chain of thought prompting, one-way and two-way. Okay, just to give you a bit of an example what the prompt is, because it's really important. This took us some time to define, because with the test and learn, we found that models could work better if you provide enough information, but accurate information. So what we did in our prompt was, okay, let's define the task. So classify the relationship between the topics. Topic A and topic B in this case are placeholder. They will be replaced with the topic in that particular request. And then what happens is that we define what are the relationships. So for example, if a topic A is a supercategory of topic B, it defines in a very precise way the different topics. And then given the previous definition, determine what is the statement, what are the possible relationships that are true. So we feed the model with likely cases, and the model has just to pick, because we understood that if we were asking the model, okay, give us the one, it will go wrong. So the more we kind of constrain the model activity, the more precise the result was. And indeed, at the end, we asked, okay, now answer by only stating the correct statement and its number. And because this will be easily to be parsed, right? Here we have got very excellent result. We test 17 models. This model differ from, large model, small model, quantized. So the first 3 are large, the other ones are small and quantized ones, and also we tried proprietary models. And of course, this is a bit obvious, especially if you work with LLMs, to find out that bigger models and proprietary ones are kind of excellent, whereas the other ones are a bit behind. But there is an interesting result here. So for example, what we observed is that Sonnet, for example, which is one of the best model, in my opinion, obtain excellent results. We are talking about 96.7% of F1 score with just one way. The moment we use chain of thought, the performance is degraded. So it looks like that chain of thought is confusing him. He wants things more to the point. However, the chain of thought prompting, while the model is asked to reason and stuff, right, favors smaller models. And because I mentioned to you earlier the fact that we want to be more sustainable, we want to be more cost effective and everything, these models nowadays are becoming cheaper and cheaper to run. So at some point, if we are able to improve the performances of this model, we are in a good position rather than using the big ones. So yes, So ongoing work, because we are also working on this as well. We fine-tuned 12 because we realized that open models is the way to go. So how do we move from here? So what we did in the meantime is to fine-tune 12 open and quantized models, so very small ones, so something that can easily run on a laptop. And then we try to we test them on IEEE for engineering, on FISH for physics, and MESH for medicine. So what we observed, this is a bit of an obvious result, is that when we fine-tune, results are higher than zero-shot learning. And this is something that kind of, I say obvious because it's something that happens in every kind of task nowadays. If you have a task and you fine-tune, of course, the model is going to be better than zero-shot learning because the model has learned something new, right? However, we didn't stop there. We tried to see, okay, if I am trying to generate a taxonomy in engineering, do I really need to have a taxonomy in engineering? Or can I use something else, for example? So what we did is this cross-domain and multidisciplinary evaluations. So what we observed is that when the model are fine-tuned on a certain STEM discipline, for example, trained on FISH, and then test on IEEE, let's say, so you are moving from physics to engineering, right? So the performances are really high. This suggests that it's not necessary to use discipline-specific dataset to achieve high performance. In a way, it's a good news because even if you don't have a taxonomy in a particular field, you may use other ones, other taxonomies in other field to kind of generate that one that is missing, which is a good thing. However, this does not stop here because when we train on multidisciplinary dataset, and here what I'm saying by multidisciplinary is that we kind of merge together FISH, MESH, and IEEE merge together as a multidisciplinary field. This dataset, when tested on individual one, produce even higher result. So the multidisciplinarity is helping a lot. Unfortunately, I cannot show you the results because the paper of this research is currently under review at the International Semantic Web Conference, which the review period started last week. So that's why I hope you can forgive me for this. And yeah, in order to conclude, also because I'm running out of time, classifying relationship between research topics is challenging. We learned it through the hard way. LLMs are great at this task, and they're better than previous solution. For example, statistical approaches, and also traditional AI. And simply because, statistical solutions are prone to the dataset, the size of the dataset, the information that you have there, and so on. So there could be issues that are related to the statistics, right? That are intrinsic to the statistics. When you use traditional AI, for example, Cybert is a good model, but what we observed is that it is really hard for it to understand exactly what a concept means. So it kind of, when we fine-tune it, it reasons mostly on a syntactic level. At least this is my point of view, in a way that, it is not really able to elaborate further on a topic. Whereas generative AI are able to understand, to define a topic, they're able to get a larger context. Okay, this is a topic, it's this, okay, maybe the relationship is this because of that, and so on. So that's why generative AI, they are better than traditional solutions. And we are glad of this result. So future work, we need to include and develop more STEM disciplines and beyond. And also we need to develop automatic systems to generate and expand and integrate KOSs, because I would like to remind you that for me, the most important thing is that we reach this objective of creating a comprehensive taxonomy or KOS of all fields that is broad enough, it's very fine-grained. Sorry, when I say broad, I mean kind of multi-field, it's very fine-grained, and we don't have to start from scratch. We can reuse stuff that is there. So an integration process is very much needed too. not only generation of relationship. So, okay, this is over from my side, and I'm happy to take questions.